So today we're going to be talking about circular motion, and specifically centripetal force, centripetal acceleration, and speed. So let's take a second to think back on Newton's laws, which we've just finished learning about, and see how is this going to tie in. Newton's first law is the law of inertia. Something in motion will stay in motion, or something at rest will stay at rest unless acted on by an unbalanced force. Newton's second law, F equals ma, an unbalanced force will cause an acceleration, and Newton's third law was action and reaction. So what does that mean here? Well, if I've got an object moving in a circular path, remember velocity is made up of both direction and magnitude. Which way am I facing and how fast am I going? So if I'm moving in a circle, the direction is constantly changing, which means that my velocity is constantly changing. And since acceleration is change in velocity, I've always got a non-zero acceleration. Now, Newton's second law says if I have a non-zero acceleration, that means there's an unbalanced force. So whenever I've got something moving in a circular path that is constantly changing direction, therefore constantly accelerating, there is going to constantly be an unbalanced force acting on that object. So think about that slice the string game or this picture of somebody doing the hammer throw. If I stop that force, if there is no longer an unbalanced force, what is going to happen? Well, it won't be accelerating inward anymore, which means the object is going to go off in a straight line. So that means that my velocity at any point as I move around this circle is tangential to the circle, or is pointing off in one direction. So as I move around in a circle, my velocity is always pointing out in a straight line, which means my acceleration is always pointing inwards. So the centripetal acceleration, or the acceleration as I go around a circle, is always pointing in to the center of the circle. And my velocity is always pointing out to the side, whichever direction the object is facing in that moment. So then we've got an unbalanced force. We call that force specifically the centripetal force. Centripetal means center seeking, because this is a force that is pulling the object towards the center of a circle. Centripetal force isn't necessarily a specific force. It is not a push or a pull or friction every time, but it is the sum of all the forces that are causing an object to move in a circle. So for example, if there is a child sitting on this swing, they might not be going in a full circle, but they are going to be making a semicircle around it. And there is tension pulling this child towards the center. So I have a centripetal force that is best represented by tension. Our equation for centripetal acceleration, since I am constantly moving and constantly changing direction, I am constantly accelerating, because changing direction means changing velocity. And the acceleration must be towards the center of the circle, since acceleration happens in the direction of net force. Remember, my force is pulling me into the center of the circle, which means the acceleration also has to point into the center of the circle. So centripetal acceleration is A equals V squared over R. Note that this is a V with a little t next to it. That means tangential velocity. That is the velocity at that moment. Remember, my velocity is constantly changing direction. So it is the velocity at that spot at that moment. And the r is the radius of the circle. Now, I know centripetal acceleration is V squared over R. Force is F equals ma. And so in a circle, the centripetal force, or the sum of all the forces that are pulling you in towards the center of the circle, is going to be F equals m times my centripetal acceleration. So I'm going to plug V squared over R in for A and get that centripetal force is equal to mass times velocity squared all over R. There are lots of examples of centripetal force in life all around you. Earth that is constantly moving in a close to circle around the sun. It is being pulled on by the sun with gravity. So gravitational force is the centripetal force. On a rope, if I was swinging my keys around in a circle, it is the tension in my lanyard or the tension in my rope that is pulling my keys towards the center. And when a car goes around a curve, it is friction on the wheels. That would be your centripetal force. Now, what is my speed at that moment? How do I find my tangential speed or my speed at a particular second? We already know that speed is distance over time, and an object that is moving in a circle travels a distance that is equal to the circumference of the circle. So a reminder from geometry, circumference is 2 pi r, 2 times pi, 3.14, times the radius of the circle. So the speed of circular motion, my tangential velocity, will be 2 pi r divided by this capital T. That capital T is different from time. It is referring to the period. The period is how many seconds it takes to complete one revolution. Sometimes this is given to you in revolutions per minute, or RPM. That is what the tachometer on your car shows, is revolutions per minute. This is something that we would need to convert to seconds per revolution. When we're working with period, we want it to be in seconds per revolution. So to get RPM, or revolutions per minute, to seconds per revolution, first we're going to flip the number upside down, and then we would just convert from minutes to seconds. So here it says 5,000 RPM. What would that be in seconds per revolution? So if I flip the 5,000 upside down, and then I'm going to multiply by 60 to convert seconds or minutes to seconds, I would get 0.012 is the period of the wheels on my car in that example. Take a second to look at this practice problem and pause it if you need to. So I've got a rubber stopper on the end of a 0.5 meter long string, completing 10 circles in 5 seconds. And I want to know the velocity of this rubber stopper. Well, if I've got 5 seconds for 10 revolutions, I'm going to do 5 divided by 10 to get that it takes half of a second per revolution. So my period is 0.5 seconds per revolution. Now I know velocity is 2 pi r over t. So I'm going to plug in what I know. I plug in 0.5 for the radius, because that's how long the string is, and 0.5 for my period. That's what I just found, to get that the velocity of the rubber stopper on this string is 6.28 meters per second. So that is, if I've got this lanyard of keys swinging around, the length of my lanyard would be 0.5 meters. And that makes the circle because it is going around. The center is at my hand. So the radius is only the length of the string, because it forms a whole circle as it moves around. So the length of the string is my radius. Take a second now to think about inner versus outer circles. And for example, this wheel. When a circular object is rotating, it takes the same amount of time for the center of the circle to complete one revolution as it does the outside of the circle to complete one revolution. So take a second to pause, think about it, talk with somebody you know. Which part of the wheel do you think has a greater speed? Well, the farther you are from the center of the circle, the farther out you are, the bigger your radius is going to be. So you've got more ground to cover in the same amount of time. So an outer circle is going to be moving faster than an inner circle. Lastly, let's take a second to think about centripetal versus centrifugal or centrifugal. You might have heard people talk about the centrifugal forces. So let's think. If I'm spinning a bucket of water around and it goes over my head, why is the water not falling out of the bucket and getting me wet? It's because of inertia. It's Newton's first law of motion. An object is going to want to stay in motion. So the water in this bucket has a velocity when it's above my head to the side. It is pointing over to the side and it wants to keep moving that way. The velocity in this water bucket is never pointing down at my head. So the water doesn't want to move down. It wants to keep moving to the side. So when it's whether it's water staying in a bucket or that strange feeling of in your gut of being heavy when you are moving around a curve quickly, some people will refer to that as the centrifugal force, where it feels like you are being pushed away from the center of the circle. This is not a real force. You would never put this on a free body diagram. It is not a true force because we cannot trace it back to something that is exerting it. It is inertia. You want to keep moving forward in a straight line as you move in a circle. And it just ends up as you move feeling like you are being pushed out of the circle. You never are actually being pushed, or the water in the bucket or anything is never actually being pushed out directly from the circle. It wants to keep moving in a straight line because of inertia, because of Newton's first law. But it is being pulled into the center. So the only force there is the centripetal or centripetal, if that's easier to say, the force that is pulling you into the center of the circle. So there is your introduction to circular motion. Next week, we're going to talk more about how a vertical circle looks different from a horizontal circle. See you later.